Hi class, so today's lecture will be about computing gains. This is a very practical exercise, and during my co-op at Bridgestone Research, I was programming controllers and I had to think about these things. So this is very practical. So thinking about the industry standard inputs or outputs from 4 to 20 milliamps, 3 to 15 psig, air to open versus air to close control valves, very practical. To illustrate this, we'll look at our temperature feedback control loop that we studied before in our realistic block diagram notes. And I'll go through the block diagram again just to remind you, but you can, of course, fast forward through that if you remember very well. So the idea is that we have a disturbance variable right here, and that's the incoming temperature of this water, right? And the water goes into this tank, and then there's this steam coil. There's a coiled pipe and there's steam inside that pipe, and that heats up the water, and the water exits at a higher temperature. And this is our controlled variable. We want to control the temperature at which the water comes out of the tank. And the manipulated variable is the flow rate of steam controlled by this control valve, okay? So the idea is if it's not hot enough, you want to bump up the flow rate of steam in order to heat up the water more. So a few other things to note. Here I'm giving you actual values. So one is the value for the input temperature at steady state conditions, and it's 30 degrees C. So I decorated it with a bar because it's steady state. And I also gave you an actual value for the set point of the temperature of the liquid coming out of the tank. That's 90 degrees C. The electrical and pneumatic signals, we're going to take them as the industry standard. So 4 to 20 milliamp, 3 to 15 psi. All right. The temperature transmitter is direct acting. Okay. So what that means is if the temperature goes up, the electrical signal coming out of it also goes up. Okay. And it has an input range of 40 to 120 degrees C. So we'll talk more about that. So that's basically the range of temperatures that it can detect. And then the temperature controller is proportional only. And I told you what its gain is. It's 2. All right. And then the bias value is set at 8 milliamps. And this is the value of P tilde such that we can maintain the set point at steady state conditions. So this results in the steam flow rate required to maintain the temperature at a set point at steady state conditions, okay? Also, the current to pressure transducer is direct acting, okay? So what that means is if we bump up the controller output, then the pneumatic signal will bump up as well, all right? Finally, the control valve is air to open, i.e. when it fails, it will close. So all of these are details that we need to account for below, okay? And we'll scroll up a bit too, so you don't have to memorize them. All right, so I thought it would be helpful to go through the block diagram with this again. So fast forward if you remember this part, all right? So first we have a set point coming in. And then through a gain, we convert the actual set point into an internal set point. And I'll decorate that with a tilde because that is a milliamp signal. So all the actual set point is degrees C. This is a milliamp signal, and that gain is what converts it to that. And we'll actually compute what that gain is in this exercise, all right? And then down here is the measured temperature, Tm, and this is tilde. We're decorating with an M because it's measured, and this is also a milliamp signal for comparing to the internal set point. All right, so and out here comes the error. That's the difference between the set point and the measurement. And now we have our controller transfer function. And here we're saying Kc is 2, it's P only. So this is a proportional only controller. So I'll say this is a P controller. And what the controller does is it outputs a milliamp signal. And that milliamp signal is P tilde. So we use P because eventually, once this passes through the current to pressure transducer, it's going to put out a pneumatic signal. All right, so this is the controller output is electrical, so is the error, and then finally the current to pressure transducer transduces that current into a pressure P, and that pressure P that then pushes on the control valve. It has some sort of dynamics, all right, So this is GV of S, V for valve. So this is your IP transducer. This is your valve. And then finally, that pressure on the valve results in a certain flow rate of steam, U star, and that's your manipulated variable. So, and then this is in kilograms per minute, flow rate of steam. And then finally, that manipulated variable affects the process, and let GU of S be how exactly the flow rate of steam changes the temperature, all right? And that's not the only thing that affects the temperature. The disturbance is also affecting the temperature, all right? So we also have a contribution to the temperature from the disturbance, and that disturbance variable is Ti. So in here, we have the input temperature, incoming temperature Ti. And so this is the contribution from the disturbance right there. And then this temperature is measured by a sensor, which might have some dynamics. So we'll call that GS of S for sensor. And the sensor outputs a measured temperature, okay? And that's in degrees C, right? This is degrees C, degrees C, degrees C. All right, and then this is your process, which is affected by the manipulated variable, and it's also affected by the disturbance variable. It's your sensor. And then finally, we need to convert the measured temperature in degrees C into an electrical representation of what the measured temperature is in milliamps, so we can compare it to the set point. And this Km has to be, this Km here, has to be the same as this, right? It wouldn't make sense otherwise, since you're comparing your set point to the actual measured temperature. So that's a review of this block diagram, and now we're going to demystify this a bit and actually compute what Km and Kip are. So the first question, determine the gain of the temperature/sensor transmitter in its units. So that's Km, okay? So i.e. find Km. So let's isolate the temperature transmitter here. This is our temperature transmitter, all right? If you go up to the diagram, TT temperature transmitter, it takes in a measured temperature, Tm. And what it outputs is, and I won't put a star on it because, yeah, so it takes in a measured temperature, and what it outputs is a milliamp signal, Tm tilde, right? All right. And so what we can do, let me put this, so Tm star, and we're going to assume that it's linear. So in this class, and often in practice, in this class, we'll assume that there's a linear relationship between the input and the output, and sensors are designed that way in practice. But of course, you need to check the manual of whatever sensor you have to make sure that's the case. But often that's the case. Okay, so let me draw a graphical picture of what this looks like. So here we have our input, which is Tm, and this is the actual temperature. And then your temperature transmitter outputs Tm tilde, which is a milliamp signal representation of your temperature. And because this is an industry standard temperature transmitter, its output is between 4 and 20 milliamps. So here's 4 and here's 20. And we also know that it's direct acting. And because it's direct acting, what that means is that as the actual temperature goes up, so does the milliamp signal. So we know the slope will be like this, okay? It's going to be linear, and it's going to have a positive slope. And as you can see from the equation on the left, this here is actually the gain Km. It's the slope of that line. Oh, I mixed up the... So the output here is Tm tilde. Yeah, so I mixed up this equation on the left. Yeah, so the slope here is Km, okay? And what we found, or what the problem statement tells us, is that the temperature transmitter has an input range of 40 to 120 degrees C. All right, so what that tells us is that this value here is 40, and this value here is 120. So this is the picture of how this temperature transmitter works. You have the actual temperature. It has a range of 40 to 120, and then the temperature transmitter maps that to a 4 to 20 milliamp signal in a linear way. All right, so, and I'll write this down, direct acting. What that means is as the input increases, Tm increases, this implies Tm tilde increases as well. So this is the output. Yes, so the increases, yeah, and that's the output, okay? And so what that implies is Km is greater than 0, as depicted in this picture here. And what we can do from this plot is compute the slope of that line. All right, Km equals change in y over change in x, right? 20 minus 4 milliamps all over 120 minus 40 degrees C. All right, so it's output, change in y, output over input. And what we get if you put that in MATLAB or Julia is 0.2 milliamps per degree C. And we can put a box around this, a red box. And just to check the units, let's check the units real quick. So this has units degree C. If you hit it with the Km, the degree C cancels, and you get milliamps, which are the units of the output. So the units make sense. All right, so in words, let me write this down. For every increase, okay, let me not say for every, for a 1 degree C increment in Tm, T tilde M will increase by 0.2 milliamps, okay? So basically what this tells us is if you see the temperature transmitter output increase by 0.2, then the temperature went up by 1 degree C, right? That's practically extremely important. And you would put this as a value in your controller. So that's what that Km is, and that has to be the same Km here that converts the set point into an internal set point in order to have a reasonable comparison between the internal set point and the measured temperature. So that's Km. Okay. So now the next question is, what is the value of the temperature transmitter when T is at its set point? So this is asking a very simple question, and we can actually copy and paste this down here. Copy, paste. And so the set point is 90 degrees C, okay? That's a set point. So the set point is right here. Let me draw in a different color. Let me draw in blue. So this is 90. I'm not sure if that's proportional. That's a set point. Equals T set point, all right? And then the question is, what is the output of the temperature transmitter at that set point, okay? And we'll call that T tilde set point because that's really the internal set point, right? Right? That's this variable right here. That's the internal set point right here. All right, and so to do that, it's really a simple algebra problem here, right? So what we can do is set up an equation, Km, that's the slope of that line. There's many ways you can do this, but this is the easiest way I see to do it. So this slope here is the slope of that green line, right? And that's also the slope of this line right here, right? And so what I can do is write change in y, which is T set point tilde, minus 4 all over 90 minus 40, right? And that gives us an equation for T set point tilde, which we can solve. So that implies that T set point tilde is equal to 14 milliamps. So that's the output of the temperature transmitter when the temperature is at its set point. So if we see 14 milliamps is the output of the temperature transmitter, that's great news. The temperature is at its set point. All right, this is the internal set point. And this is equal to, conceptually equal to, the output of temperature transmitter when T, temperature of the water or liquid, is equal to its set point, which equals 90 degrees C. All right, so that's the internal set point. Okay, and now it says now it's asking what is the gain of the current to pressure transducer, i.e., KIP. All right, and so again, what we'll do is isolate the current to pressure transducer. Here's your current to pressure transducer. If we scroll back up to the figure, what it takes as input is P tilde, the output of the controller, and outputs P. All right, so it takes in P tilde and outputs P, right? And this has units milliamps, and this has units PSIG. That's what it looks like. And so then P equals KIP, P tilde. So again, we're assuming the current to pressure transducer is has a linear relationship between its input and output, which in practice they do. So here's what it looks like. We'll have the input, which is P tilde, and this is milliamps, and we'll have our output, which is P and PSI. All right, and again, this is direct acting. And what that means is that KIP is greater than 0, because if you increase the input, then the output, P, increases as well. So it's going to have a positive slope. And this is the industry standard for the milliamp signal. So 4 to 20, all right? And those milliamp signals are mapped to 3 to 15 PSI, right? And it's direct acting, so again, we'll have, let's go up there. Oh, it's not quite linear, but yeah. So that's what it looks like. And so actually, current to pressure transducers, no matter the problem, if they're the industry standard, they're going to have the same value of KIP, the same gain. So we can compute KIP, which is just a slope here, as change in y over change in x. So it's 15 minus 3 psi over 20 minus 4 milliamps. And what we'll get, and we'll see this value a lot, is 0.75 psi per milliamp, all right? And that's KIP, so we'll put a box around that. Let's put a box around this. Good. And then, so this is, I'll make a note, this is the industry standard KIP. And what this means is that if P tilde, the input to this, increases, if the controller output increases by 1 milliamp, P will increase by 0.75 psi, okay? That's what that means. And again, we can check the units here. So this has units psi, right? And if we hit it with KIP, the input has units milliamp. If we hit it with KIP, the milliamp cancels it, and we get PSIG, which is the output. So the units make sense. The units are consistent with our formula here. All right, finally, we can write the control law. It's a proportional controller that relates to controller output, right? So this is the controller output to the measurement in electronic form. So let me write this. So this is the controller output to the measurement the measurement in electronic signal form. So again, we'll write our temperature controller. Temperature controller. It takes as input Tm. Oh, whoops. It actually takes as input error. Sorry. Error, and this is in a milliamp signal. And it outputs another milliamp signal, which is a representation of the pressure. So we make it P tilde. An error is defined to be the set point, which is the internal set point, minus the measurement. So T tilde, the internal set point, minus T tilde M. So again, this is the internal set point, all right? And you can see this in our block diagram here. The error is the internal set point, it's got a plus, minus the measurement in electronic form. So that fleshes out from our block diagram. All right, and it's a P-only control law, so what we have is P tilde equals the bias value, P tilde bar, that's our bias, plus Kc E of T, right? And so we'll think of these, I'll decorate these as functions of time to be clear. So this is P tilde as a function of time. All right, this is a constant. The error, however, is a function of time. Kc we found is 2. And the bias was given to us in the problem statement. That's the value of the controller output that we need to maintain steady state conditions. It's 8 milliamps. So this is equal to 8 milliamps plus 2. And the controller gain here is actually unitless. And then the error is the internal set point, which we've computed above, 14 milliamps, minus whatever that measurement is, Tm tilde of T. And it's a function of time, right? It could be changing with time. It will be, probably. All right, so that's really our control law. Voila. So this is a very practical control law. So this is a milliamp signal output from the temperature transmitter after it goes through the conversion. So this is the milliamp signal output from the temperature transmitter. Okay, and you can see here, here's a temperature transmitter, and it's outputting this, and it's fed to the controller. Okay. Yeah, so that's a very practical P control law. So Kc, which equals 2, and it has units of milliamps to milliamps, is unitless. So I didn't miss units in the problem statement. See, because this has units milliamps, so does the output. Okay, so this is a practical P control law. That's what one might actually look like in the computer. All right, so the next question, at what critical temperature would the control valve reach its fully open position? So we want to know when the control valve saturates, basically. All right, and the control valve, we said was air to open, right? Air to open or fail close. And that implies if it's fully open, then the pressure, the pneumatic signal on it, must be 15 psig, right? All right, and this 15 psig, what this is the signal out of the current to pressure transducer, right? So now we need to trace our way back. So tracing our way back. So if the output of the current to pressure transducer is 15, which is right here, then that means that P tilde, which is the output of the controller, must be 20. Right? Because we're right here on this. We're right here. So P tilde equals 20 milliamps. Okay. And this is the signal out of the controller. Right? Okay, and now we trace our way back one more step, right? And so if that's a signal out of the controller, well, we have our control law, right? To satisfy control law, that means 20 milliamps is equal to, and we'll look at our control law, 8 plus 2 times internal set point, 14, minus T m tilde. And what we can do then is then solve for what Tm tilde is, okay? So what this implies is Tm tilde, so 20 minus 8 is 12, 6 is 8, Tm tilde. What that implies is Tm tilde equals 8 milliamps. And what this is, so I'll highlight this, that's a signal out of the temperature controller. If we trace our way back even more, Tm tilde is a signal out of the temperature transmitter, okay? So we're not quite at the actual temperature yet. So this is a signal out of the temperature transmitter. Okay? Okay, so if that's the case, then let's look at the temperature transmitter. So what must the temperature be for Tm tilde equal to 8 milliamps? So what we need to do is go out to our analysis of the temperature transmitter, which is right here. So I'll copy and paste this. All right, so I'll make a little graphical depiction for you here. All right, so now what we know is that T tilde is 8, okay? So we'll put 8, I'm not sure if this is proportional, right? And this is Tm, and we want to find out what this value is, okay? And so again, what we can do is we know what Km is. Whoops. Okay, we know what Km is, and it has to be equal to the slope of that line. So we'll say Km which is equal to 0.2, and the units here are milliamps per degree C. That's equal to the slope of that yellow highlighted line, right, which is 8 over 4, 8 minus 4 milliamps. Over Tm minus 40. And that's in degrees C, okay? So that gives you an equation for Tm. So that implies what Tm actually is 60 degrees C, all right? So this here must be equal to 60 degrees C, okay? So, and what we've just done is arrived at the correct answer, because what this is asking is at what temperature would the control valve be? This is a critical temperature where the control valve reaches fully open position, and we found it, right? It's 60 degrees C. So what that tells us is that 60 degrees C, and that's below the set point, is the coldest this water can get before the valve is fully open. And if it gets colder than that, the valve will remain fully open and we can't take any more controller action. So it's basically saturated once you get that cold. So the valve is fully open. When we measure the liquid in the tank to be 60 degrees C, right? And that's colder than the set point. Set point's 90, so that makes sense. So then you're fully open and blasting steam through that coiled pipe. So this is extremely practical to know, right? Because you know if it gets even colder than that, you can't take more drastic control action. Your valve's already fully open. All right, so I reasoned through, so I gave you the gain is positive 2, but now I want you to reason through that this gives us the correct controller action, okay? And the way to do this is, what we do is we say, we just make up a hypothetical situation and figure out if it makes sense. So let's say that the error E of t, okay, this is the set point, the internal set point, minus the measurement, right? Let's say that this is greater than 0, okay? And what this implies is that T set point is greater than Tm tilde, okay? And since the temperature transmitter is direct acting, which means Km is greater than 0. What this means is that the temperature of the liquid is too cold. Or Tm is less than Tm set point in the degrees Celsius units. All right, so the liquid we know is too cold, okay? And so what we want to happen is we want valve to open to increase the steam flow rate and make the liquid hotter. And heat liquid. All right, so we want the valve to open more because the liquid is too cold, all right? And now, because the control valve is air to open, if we want it to open, we want the pneumatic signal P to increase. All right? And since the current to pressure transducer is direct acting, i.e. KIP is greater than 0. What that implies is we want the controller output, which determines P, to increase, right? All right, so now finally we've reached a controller, and then the control law, which is P equals P tilde bar plus KCE. So this term here, the error is greater than 0, right? By our supposition, right? And so what we conclude is P tilde will increase, or it will be bigger than P than the bias. Will increase so but what I mean is P tilde will be greater than their steady state value if and only if Kc is greater than 0, right? Because then we'll have a positive term here, right? So basically, what we've shown is that, yes, in order to have corrective controller action, the controller gain has to be positive. If the controller gain were negative, think what would happen. What would happen is P tilde would decrease, and then what would happen is the valve would close and exacerbate the situation. and it would take the opposite action as what's needed. So this is the logic that you need to do. You need to walk through each step of the process and think about the directions that each are acting based on our input and output relationships. But I just gave you the control gain in this one.